Hello and welcome to G Fun Facts Online. Today we are stepping inside the control room of a machine that builds stars. We are going to talk about a specific Wednesday afternoon, February 12th, 2025, and a number that looks like a glitch in the simulation but represents one of the most significant leaps in fusion energy history. That number is 1337. On that afternoon in Catarache, southern France, a hush fell over the scientists and engineers monitoring the West tokamak. They were watching a monitor displaying the heartbeat of a superheated loop of plasma. 10 minutes passed, then 15, then 20. By the time the plasma finally extinguished, the clock had stopped at exactly 337 seconds. For those of you who grew up on the early internet, 1337 spells out elite in leet speak. It is a funny coincidence, but for the physicists at the French Alternative Energies and Atomic Energy Commission and the Princeton Plasma Physics Laboratory, it was much more than a meme. It was the moment they shattered the Tungsten Wall. This 22-minute and 17-second run didn't just break a world record. It proved that the specific design chosen for the massive international ITER project actually works. To understand why this is such a massive deal, we have to back up and look at the vessel problem. We often hear about fusion in terms of temperature, 100 million degrees hotter than the core of the sun, but we rarely talk about what you put that hot star inside of. You need a magnetic bottle, a tokamak, to hold the plasma. But that magnetic cage is never perfect. Stray particles, high-energy neutrons, and intense radiation are constantly smashing into the inner walls of the reactor. This interface, where the fourth state of matter meets solid metal, is arguably the harshest environment in the known universe. For a long time, the material of choice for these walls was carbon, graphite. It seems counterintuitive to build a sun inside a fireplace material, but carbon is actually very forgiving. It doesn't melt, it sublimates, it handles thermal shock well, but carbon has a fatal flaw that makes it impossible for commercial energy. It is a sponge for tritium. Tritium is the heavy hydrogen isotope we need for fuel. If you build a commercial reactor out of carbon, your walls will soak up your fuel supply and become dangerously radioactive. You simply cannot run a power plant where the fuel disappears into the bricks. The alternative is tungsten. Its chemical symbol is W, from the German Wolfram. It has the highest melting point of any element in the universe, at 422 degrees Celsius. It conducts heat beautifully, and most importantly, it does not absorb tritium. It seems like the perfect armor. But tungsten has a dark side. It is what physicists call a high Z material. It has a very heavy atomic nucleus. If a carbon atom flakes off the wall and falls into the plasma, it burns up harmlessly. But if a heavy tungsten atom falls into the plasma, it acts like a radiator. It doesn't burn. It strips heat from the core and blasts it away as X-rays. It cools the plasma from the inside out. If too much tungsten gets in, the temperature crashes, and the fusion reaction dies instantly. This is the tungsten wall. For decades, skeptics argued that you could never run a stable reactor with tungsten walls because the plasma would inevitably poison itself. This brings us to the machine of the hour, WEST. The name stands for Tungsten Environment in Steady-State Tokamak. This machine is actually a reincarnation. It used to be a famous reactor called Torre Supra, which started back in 1988. In 2013, they gutted it and rebuilt it with a specific mission to look exactly like the ITER reactor on the inside. ITER is the $25 billion experiment being built just down the road. ITER made the bold choice to use a tungsten diverter, that is the exhaust pipe at the bottom of the reactor where heat and ash are funneled. The scientific community needed to know if this configuration could survive before turning on the big machine. The engineering inside WEST is staggering. The diverter plates at the bottom are made of thousands of small tungsten blocks. They are actively cooled by a high-pressure water loop. The heat load on these plates can reach 10 megawatts per square meter. That is roughly the same heat load as the surface of the sun, or what a spacecraft experiences during re-entry. But WEST has to endure it continuously, not just for a few minutes. So how did they achieve the 337-second shot? How did they stop the tungsten from killing the plasma? It took a combination of brute force engineering and extremely clever physics tricks. The run began at 2 p.m. The central solenoid fired, turning hydrogen gas into pink plasma. But a central solenoid is like a transformer. It can only drive current and pulses. To run for 20 minutes, you need a different way to push the electricity. The team used something called lower hybrid current drive. Think of the plasma current as a merry-go-round. Usually, you spin it by hand. But the lower hybrid system is like standing there with a high-pressure fire hose, spraying the merry-go-round to keep it spinning. They beamed 3.7 gigahertz microwaves into the plasma, pushing the electrons continuously. But the real magic was in how they managed the wall. The team, supported by researchers from Princeton, used a technique called boronization. They dropped boron powder into the plasma. Boron is a light element. It coats the tungsten walls, creating a sacrificial shield. It acts as a buffer, preventing the heavy tungsten from sputtering off into the core. Simultaneously, they used a specialized X-ray camera to watch the plasma's temperature profile in real time. If the camera saw a tungsten impurity building up in the center, the control systems could tweak the magnetic fields to flush it out before it caused a collapse. As the clock ticked past 500 seconds, the room shifted from tension to excitement. At 500 seconds, the plasma had reached equilibrium. The walls were fully saturated with heat, the water cooling was holding steady, and the feedback loops were locked in. At that point, the physics stops changing. If you can hold it for 500 seconds, you can theoretically hold it for days, provided your machines don't break. They passed the previous record of 1056 seconds set by China's East reactor. When the system finally ramped down at 337 seconds, it wasn't because of a crash. It was just the end of the scheduled window. This result is a green light for the world's energy future. It de-risks the ITER project, proving that the tungsten diverter isn't a showstopper. It proves that we can actively manage impurities and handle the heat flux of a commercial power plant. We now know that we can build a vessel that doesn't just hold a star for a few seconds, but can constrain it, cool it, and harvest energy from it for long durations. The tungsten wall has been breached. The era of the carbon experiment is ending, and the era of the metal power plant has begun.